Hello everyone, welcome to now chapter 8 part 2, periodic table trends continued. So first let's talk about the Pauli Exclusion Principle. So remember when we talked about the coordinates for the electron using the quantum numbers? Well, it turns out now we're going to talk about that fourth variable or coordinate, and that electrons, they'll have four quantum numbers that they can be identified by, but they can't have the same four quantum numbers, and that's why orbitals have some rules where only two electrons can occupy a single orbital. So it's kind of like that train analogy I mentioned. Like in each cart or a train, there's an aisle, and then like in a particular section of the cart, there's only like 2 seats per row, and then there's only 2 people can occupy a certain row on a train. So only 2 people can occupy that. So it's kind of similar to an electron occupying an orbital. The last number represents what seat you have, and then in a specific row there's only 2 possible seats, or a specific section of the train cart. Okay, so it's kind of like that. We could kind of relate it back to that. So what this means is that no more than 2 electrons can occupy an orbital. If there are 2 electrons in the orbital, the spins must be paired. So they must be have opposite spins. So electrons typically have spins of plus 1/2 or minus 1/2. And the 1/2, it's basically it's a spin quantum number. So it's kind of a fact of nature that, okay, they precess around this axis, and they have a spin quantum number of 1/2 or negative 1/2. So atoms with an odd number of electrons are paramagnetic, meaning that not all the atoms in the electron are paired with another electron in the same orbital. They will interact with a magnetic field, and that's what causes magnetism. So atoms with an even number of electrons are said to be diamagnetic, meaning that all electrons are paired and they will not interact with a magnetic field. Okay? Now we can specify electrons in atoms with 4 quantum numbers. So we can now give them all the coordinates they need to describe individual electrons. So here are the allowed combination of quantum numbers for n equals 1 through 4 shells. So for 1, you can only have 1, 0, 0. So the only other quantum number that an electron can have is either 1/2 or negative 1/2. So only 2 electrons can have those set of quantum numbers. Okay, then for the 2 level, we can have 6 possibilities. 3 for the third energy level, 10 possibilities, and then for the F orbitals, 14 possibilities. So these set of quantum numbers, they may look like code or something, but they're just specifying, what energy level the orbital's in, the kind of orbital electrons look in, and then ML, the orientation of the orbital, what direction is it facing, and then lastly MS, what kind of spin does the electron have in the orbital. Okay, so here are a combination of quantum numbers here. Okay, so on this lower half, we have all the quantum numbers here. On the upper half, those are forbidden. So for L equals 1, you cannot have there's no 1p, there's no 1d, there's no 1f, and there's no 1g. Okay, so these are the forbidden quantum numbers here in the turquoise blue there. So it starts at 1s, 2s, 2p, 3s, 3p, 3d, 4s to 4f, 5s to g, 6 to h, and then 7 to h, and 8 to h. So there may be higher ordered orbitals, but I don't know if there's ever been a case past h. So, but there's no element that even has a g orbital yet. So we haven't determined any elements that actually satisfy these quantum numbers. Okay, so the order of filling, it goes along with the periodic table, but we can also think about this diagram here on the right, the order of filling. where electron fills the orbitals. It goes from 1s to 2s, so kind of the zigzag line right here. 2s to 2p, 3s, 3p, 4s, 3d, 4p, 5s to 4d, 5, then it's 5p, 6s, then 4f, 5d, 6p, 7s, 5f, 6d, 7p, then 8s, and so on. Okay? All right, so now let's predict electron configurations here. Okay, so let's predict. So, like I did on the periodic table in the last lecture, I labeled all these orbitals here. So you see here, we can label the S here, 1s, 2p block, 3d block, and the F block. So those are the blocks we will need to know to write electron configurations. Okay. All right, so now let's predict the electron configuration for a neutral tin atom. So tin has Z equals 50. Oops. All right. So let's get out our periodic table. Tin has the atomic number 50. So let's mark on our periodic table where tin would be. So let's go back to the periodic table. So we look at tin, right? So tin is right here. Whoops, might need our pen to... So it's going to have all the electrons that came before it. So from helium to neon to argon to krypton, all the way up to indium. So it's going to have the electron configuration of indium plus one more electron. So it's going to be, in this case, going to be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, and then 4p2. Okay, so we'll get a lot of practice with this in discussion. All right, so let's go back to the lecture now. Okay, boom, 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 boom. Okay, let's see here. So let's go back here. So we will have 1s2, 2s2, 2p6, okay, 3s2, 3p6, 4s2, 3d10. So we're just going in the order that we saw up here. 3d10, now 4p, 4p6, 5s2, so we're going to 5s2 now, then we're going to 4d10. So it could be very long in certain cases. All right, and then 5p2. Okay. So we can also abbreviate the electron configuration as well. If we go back to our periodic table, let's see here. So if we go back to our periodic table, we can look at the noble gas configuration that came before tin. So that's the principal energy level before the n equals 5. So it's krypton here. So what we can do is abbreviate our electron configuration by saying, okay, this has the electron configuration of krypton, which is up to 4p6, and then we could write 5s2, 4d10, and then 5p2. Sorry, not 5p2, 5p2. So from electron configurations, we can actually figure out how many valence electrons each element has. So in this case, tin is the valence shell is at the 5th level, so valence. So this has a valence, so n equals 5 is the valence shell. So in this case, we count up all the electrons from the 5 energy level, 2 plus 2, so this has 4 valence electrons. It makes sense because tin is in the same group as carbon, so it has 4 valence electrons. So that's how we would count valence electrons. Something we'll have to be able to do in the next chapter when we talk about Lewis structures. Okay. All right. So with everything else in chemistry, you know, there are some exceptions. There's always a case where there's an exception. Okay. So one thing we can do is we can condense the electron configuration by writing a noble gas configuration. So we can use the noble gas notation here to abbreviate the inner core electrons. So for example, lithium, we can say, okay, it has a electron configuration of helium and then additional electron in the 2s level. So we could represent, you know, the lower filled s and p orbitals, and with the noble gas notation there. So for all these elements on the second row, we could all write helium because we know it has the filled s shell of helium, and then what's left is the valence shell of electrons, so 2s and then 2p, like so. Okay, so 2s, 2p. And then we see the valence electrons. As we go across the periodic table, the valence electrons increases by 1. So 2, 1 for lithium, 2 for beryllium, 3, 4, 5, 6, 7, 8 as we go to neon. Okay? So there's also a pattern within the vertical columns or groups of the periodic table. So the elements in a group often have similar configurations for their outermost or valence electrons, okay? So we can confirm this by looking at the electron configurations of the elements in the columns on either side of the periodic table. So for example, group 1, see here, they all have configurations of S1. So they have 1 valence electron. So, and then group 7A, they have a configuration of S2P5. And you see there's 7 valence electrons. So there's a neat pattern with how they're arranged in groups. They have the same outermost valence electron configuration. So it'll be S2, S the highest level, 2s2, 2p5 for fluorine, and then one group down, one period down, 3s2, 3p5. So it's very there's a pattern to these arrangements here. And then you see potassium also, S1, rubidium, S1, cesium, bromine. You see here it has still the S2P5, S2P5 for iodine, S2P5 for astatine, I think. So what comes in between them, the 4Fs and the 3Ds, 4Ds, those are considered still the lower energy levels, so they're not considered the valence shell. So that's why we don't consider them in the pattern here. Okay. Let's predict the electron configurations for calcium and zinc from their positions on the periodic table. I'll say. Okay, so calcium is, so let's take a look at our periodic table once again. So calcium is right here. So here's calcium. And then we're looking at, I believe, was it zinc? Zinc right here. So we could write the electron configurations. Calcium would go from calcium, zinc, the noble gas that precedes them in the third row is argon. So we can abbreviate their electron configurations with the argon notation. So let's do that. Okay. So for calcium, so let's write for calcium, we have argon. And then for calcium, we saw that it's in the second column on the periodic table. So we could write 4s2 because it begins in the fourth row, 4s2. And then for zinc, we're going to have 10 more electrons from calcium. So zinc would have argon, 4s2. Okay. And then zinc in this case has 10 more electrons, right? So it's going to have it will complete it will have a filled 3d subshell. So 10 electrons from the d orbitals, and we get 3d10. Okay? So there's two ways you can do it. You can count how many electrons from, maybe a noble gas has, and then count how many additional electrons that element has. Or you can just look at the periodic table and figure out, okay, which position does my element occupy? And you would count the number of electrons and fill out the sublevel based on that number. Okay, so zinc, argon, 4s2, 3d10, calcium, argon, 4s2. Okay. So, now let's do this example. How many unpaired electrons are there in each of the following atoms? Which of these atoms would have magnetic properties? So carbon, remember carbon is in group 4. Period 2. So carbon would have a 2s and then some 2p orbitals. So we're going to fill up the 2s first. And then here's the 2p. And when we fill out the 2p orbitals, we're going to maximize the spins first in each orbital, then pair them up. So that's called Hund's rule. Well, actually, now I've added too many electrons. So remember, carbon has 4 electrons. Sorry, not 4 electrons. Carbon will have 4. It has 4 valence electrons, right? So the valence shell is the second energy level. So we're going to add 2 more electrons in the p subshell, and so we get 2 unpaired electrons. Okay, so this will be a magnetic compound. So it's magnetic because it's paramagnetic. It has unpaired electrons. Okay. How about nitrogen? So nitrogen is in group 5, right? So it has 5 valence electrons. Group 5. It's also in period 2. I think all of them are in period 2. Okay. So let's just draw the 2s at lower energy, because remember, the lower energy orbital gets filled first, and that's why the 2s gets filled first. So it has 5 valence electrons, so we're going to fill out all the electrons of the 2p, so we have 5. So it has 3 unpaired electrons. So nitrogen will also be magnetic and paramagnetic. All right, how about neon? Neon is in group 8, but also period 2. However, with neon, now has 8 valence electrons, and if we use the 2p and 2s orbitals, we'll have a filled shell. So now all the electrons are paired. So 0 paired electrons. 0 unpaired electrons. Okay. So in this case, this will be non-magnetic or diamagnetic. And then lastly, we have fluorine here. Fluorine is in group 7. Also period 2. In this case, fluorine will also have unpaired electrons. Because it has 7 valence electrons, right? So we're going to have 1, 2, 3, 4, 5, 6, 7. So it has 1 unpaired electron, so it'll still be magnetic. Okay? So that's how we determine the sun's paramagnetic or magnetic. Look at the unpaired electrons. So when you're filling out these orbitals, you don't want to maximize you don't want the pair electrons until all the orbitals have been occupied by 1 electron each, because that gives the lowest energy arrangement of the atom and its orbitals. So always maximize the spin. So fill empty orbitals of same type first with 1 electron each. Okay, so that's a general rule we should always consider. All right. So now let's move on here. So now we're going to talk about why we do it this way. Okay. So, but we'll pick that up in the next video, okay? So we'll start talking about orbital filling diagrams and Hund's rules. Okay? See you everyone.